Welcome back, my little linear algebra babies, to Chapter 2, Section 2. And we're going to see some consequences of, or some applications that are born out of those matrix operations that we were discussing in 2.1. So let's jump in. Let's assume that you are in the market for a new computer monitor or in the market for a new television. And someone tells you that you need to go full HD. And you say, well, what's that? And they say you need to go 2K. What's that? They say you need to go 1080p. Okay, so what's that? So 1080p. So how do we think about this? How do we think about this resolution that this individual is telling that the minimum that you need of resolution? Well, 1080p can be thought of as having 1,920 pixels running horizontally across your screen and having 1,080 pixels running vertically down your screen. Now, a simple multiplication, 1920 times 1080, would give you about, well, a little bit over 2 million pixels. Right, assuming my arithmetic is correct. And then you might ask, well, what the heck is a pixel? Well, a pixel is just, let's just say, a tiny little area, a little minute area that can be illuminated. Right? So it's just a tiny area of illumination. So let's take a look at how it is that you get all these beautiful colors on your TV. And more importantly, how it is that this can be thought of as matrices. Well, I think you've already seen from my example of how to interpret 1080p, that is really just a large matrix, right? A 1920 rows by 1,080 columns. But what's interesting is when you take these pixels and you think of, we think of each little individual pixel inside that TV. Well, each pixel has what we call 3 subpixels. Right? So red, blue, and green. So 3 subpixels. But what is interesting is from just those 3 subpixels, depending on just how you adjust the voltage, you can change the shade, the various colors of red and the various colors of blue, various colors of green. In fact, as always, fact check me and make sure I'm correct here, but I believe that you can get about 256 different shades of red, blue, or green. Right? So that's, if you multiply those, that's a little bit over 16 million. Actually, it's almost 17 million different colors. Hold on. Have you started daydreaming? That's almost 17 million. I think it's 16.8 million colors that can come in this one little pixel. And you have over 2 million of them in this 1080p. Now, what's interesting, how do you adjust that voltage? Well, that's basically each little pixel is going to have you have to have quite a lot of transistors running across your screen. The math is not that bad. If you just take the number of pixels you have, multiply it by the number of subpixels that you have, it comes out to over 6 million little transistors that you're going to need running across your television so that you can adjust the voltages of these subpixels, red, blue, green, in order to get the beautiful picture that you are looking at right now. Okay. So how do we adjust a pixel? Right? So let's take a look at this example. Now, it didn't show up very well when I copied and pasted it, so I went back in and filled it in. So it says the letter L, right, that you can see from this figure right here. The letter L is shown in using 9 pixels in a 3x3 grid, right? So this is a 3x3 grid, and inside that 3x3 grid there's 9 pixels. Now the colors possible on the grid are here, right? This is you don't have the 16.8 million colors that choices that you have on probably that you have on your laptop or computer that your display that you're looking at right now. You only have 4 different colors: white, light gray, dark gray, black. And each one can be represented as a number: 0, 1, 2, 3. Now, part A, our job in part A, is to find a matrix that represents that, let's say, digital photograph of this letter L. Well, that's easy. That's easy. I mean, if we go through, if you think about it, this would be represented by 2, 2, 2, 2, right? Those are dark grays. And then the light grays would be represented by 1s. So if you were building a matrix for that small little 9 pixel 3x3 grid, the way it sits currently would be look like this. But what you decide to do is, you know how you get into your editing and you start touching up your photos and changing things before you post them on your social media site. You decide to start changing some things around, maybe. So let's just take this letter L. It says, part B, increase the contrast of letter L by changing the dark gray to black and the light gray to white. Okay, so what we now want, let me start with what we want. What we now want is all of the dark grays to be black and all of the light grays to be white. So, in other words, we want the dark grays to be black, so we want 3s here. And we want the light grays to be white, so we want 0s everywhere else. All right, and now the question becomes, how do you go from what you have now, part A, to what you want in part B? Right? How do you adjust that contrast? How do you increase that contrast of that letter L? Well, we can think of it as simply adding another 3x3 matrix. Right? It makes perfect sense. If you want your 2s to be 3s, you want your dark grays to be blacks, then you're going to want 1s here. 2 plus 1 is 3. But now, since you want your light grays to be whites, you're going to want 0s, then you're going to want negative 1s everywhere else. And that's it. That's the gist of that question. Let's take a look at another application. Right? Just basic applications of some of these matrix operations. So the following example. So let's take a look. It says the quadrilateral that we're seeing here in figure 8.10 can be represented by matrix A. Now notice that the rows row 1 represents the x coordinates, and row 2 represents the y coordinates. So if you wanted to graph the point -2, -3, you can see how that's just an x coordinate, y coordinate inside this matrix. All right, so I think we got the gist. It says each column in the matrix gives the coordinates of a vertex. So all they're given to us is just the vertices of this quadrilateral, right? The corners. And our job is to use those matrix operations that we were talking about in the previous section and answer some of these questions. So what we want is we want this quadrilateral to move 4 to the right and 1 unit down, right? You're doing some animation work, and you want your quadrilateral to move to the right and then move down. Well, let's figure out what we would have to do. Well, the beautiful thing is, if you want to move your matrix, I should say, if you want to move your quadrilateral, it's just a matter of adding a matrix to it, right? And it's fairly simple. Let's make sure we understand. If you want it to move 4 to the right, then what we're going to want is we're going to want 4s here along that first row. That makes perfect sense because adding 4 in the x direction would move the quadrilateral to the right. But you also want it to move in the y direction down 1. So you're going to want -1s here. All right, so I'm not going to go through and regraph, but the result would be 2, -4, 3, 1, 7, 3, 5, -3. That would, if you were to plot these new x, y coordinates, your vertices, you would have your quadrilateral that is moved 4 to the right, 1 down. Part B, we're going to skip C, but part B, it says you now want to shrink the quadrilateral to half its perimeter. Well, obviously adding, subtracting one matrix to another matrix is not going to do that, right? If you just want to move it around, then adding, subtracting these matrices, that works perfectly. But to actually adjust the perimeter, right, you're going to need to scale. So you would actually have to, so this C represents some type of scalar. You would actually have to scale matrix A in order to adjust its perimeter. That would shrink it or grow it, depending on the value of C that you choose. But since you want half the quadrilateral to have half its perimeter, then really what you're just saying is let's just take a scalar of 1/2, multiply it by A. All right, so I'm going to go ahead and give you that result, but I'm not going to go through the details of the how because we've talked about it before. So multiplying all of matrix A by 1/2, assuming that I can actually do arithmetic correctly, should give you the following. And if you were to replot these points, you would now have a quadrilateral with half the perimeter that it had before. Okay, so now on to inverses. So what do I mean by the inverse of a matrix, right? So maybe we should start with what we know, right? So let's start with what we know. So if I wanted to, or let's just say I were to ask you about the inverse of 1/3, right? Well, a lot of times we use the term reciprocal when what we actually mean is the multiplicative inverse. And one of the properties, one of the key features of this multiplicative inverse is the following, that if you take any number and multiply it by its, if you take a number and multiply it by its multiplicative inverse, what do you get? Well, you just get 1. Okay, but wait a minute. What is the matrix analog of 1? Right, so remember, the matrix analog of 1 was that identity function. So we can say in a 2 by 2, the identity function would look as follows. So, all right, so let's think about this a little bit farther. I'm going to erase what I just wrote. So we're looking for a how-to guide for taking inverses of matrices, if we can take the inverse of a matrix. And we want it to, clearly we want it to preserve this, the property that when you multiply any number by its multiplicative inverse, you get 1. That's the goal. So before I do that, let me look at, let me first erase what I have here. And let's take a look at how you would solve this basic equation for x. All right, so we have 3x is equal to 6, and you're asked to solve for x. Well, I understand that the first step would be to divide both sides by 3. And that would leave you with a result that x is equal to 6 over 3. Right? But now I halt there for just a second, because I'm trying to show you something. So the idea is that if you what we want to think about is how we can use this inverse, this multiplicative inverse, if we were actually wanted to solve this equation for x. And then more importantly, we want to be able to apply it to how do we use it to solve equations for dealing with matrices. Well, let's start with the idea that 1/3 of 3, my apologies here, 1/3 of 3 is equal to 1. So in this case, if we were trying to solve, you could also think about taking the inverse of both sides of this equation, right? So let me give myself some space. So back to the equation. You want to solve 3x equals 6. But we don't want to divide both sides by 3. Again, what we're going to do is, what if we multiplied both sides by 1/3? Right? In other words, we multiplied both sides of that equation by the multiplicative inverse of 3. And what do we get? Well, what we know is 1/3 of 3, any number multiplied by its multiplicative inverse is 1. And finally, 1/3 of 6 is 2. So next, my apologies, how do we think about that when we're not dealing with equations, but instead we're dealing with Instead, we're dealing with matrices. So let's establish some things. So in this example here, A represents some m by let's say A represents some matrix, right? We'll come back to the order, right? The X in this case would represent some vector, and in this case B would just simply represent the product of A multiplied by that vector. All right. So if you want to solve for X in this case, given the fact that if there is a way of finding an inverse of matrix A, then what we know is that since any number times its reciprocal is 1, any number times its multiplicative inverse is 1, then if there is such a thing as an inverse of matrix A, we're going to denote it like this, then it should make sense that A times A inverse gives us 1. All right, which we're going to use I to represent the identity matrix. Likewise, if the order in which we perform the multiplication should not matter, right? 1/3 times 3 is 1, or 3 times 1/3 is 1. So coming back to my equation, AX equals B, if I want to solve for X, then all I need to know is the inverse of A. And if I know the inverse of A, then I can just simply say A inverse multiplied by A times X, and then take A inverse and multiply by B, right? Now, A inverse times A, we've already established that that is just I, the identity matrix. So I times X is equal to A inverse times B. And what is the identity matrix? It is the analog, the matrix analog of the number 1. So anything times 1 is itself. So what do we get? We get X is equal to A inverse times B. Now that's actually really interesting, because what you've just done, in case you started to drift on me, what we just showed is that you now have another way of solving a system of equations, right? We learned, you think about elimination methods, substitution methods. You learned how to row reduce matrices. We're throwing another way of solving a system in the mix. But all of this depends on the notion that we actually can find the inverse of some matrix A. And that is where that's where we turn to next. So how do you actually find the inverse of a matrix A? So this question depends, right? It depends on the order or the magnitude, the dimension of your matrix. So for example, if your matrix is a 2 by 2, then theorem 4, which I'll produce on another page, is the way that you can go about finding the inverse of matrix A. Right? So just notice what they're doing is they've established the entries as A, B, C, D, and here is your formula for finding its inverse. Now, the caveat at the bottom makes the statement that A times D, right? So A times D minus B times C cannot equal 0. We actually have, and you can see that that's not some arbitrary rule. You can see that right here inside of the formula for the inverse, you're going to end up having to divide by 1 over a times d minus b times c. So if you were to get a value of 0, then your inverse is not going to be defined. So we actually have a name for that, right? So we have a name for this a times d minus b times c, and we call it the determinant, right? The notation is det, so the determinant of a. And for right now, we'll come back to determinants later in a little bit more detail, but for right now, let's the thing that we want, the property of this determinant that we care about is that it not equal 0. Because if it equals 0, then we cannot find the inverse of a matrix A. All right, let me go a little bit further here. Let me give you just a couple quick definitions. So the definition of a singular matrix, right, is a matrix that is not invertible. And a non-singular matrix is a matrix that you can find the inverse, right? It's an invertible matrix. All right. So where are we going to go from here? Well, we're going to do a couple things. I'm going to practice with just this idea of how to find I want to talk a little bit more about the structure of finding the inverses of matrices. But then probably in a second video, I'm going to come back and I'm actually going to sell you on the idea of why you would want to find the inverse. And for just a teaser, because I know you're on the edge of your seat in anticipation, I'll give you a cool application. If you've ever thought about creating let's say a secret language between you and a friend, or something like that, right? So if you wanted a language that it would be encrypted to anyone else, indecipherable, and yet you and this other individual could carry on in conversation. Well, although you might argue that math is a language, Chomsky has a very interesting quote about mathematics being a language, but although you might think of mathematics as a language, it is not a spoken language. So I can't help you create a spoken language that you can use with your friend, but I can help you create a way of encrypting a message and being able to send it to a friend that will have a key who can then decode whatever message you sent. All right? But first, we need some structure. We need some how-to. So the following example asks a very, very simple question. It just asks, given these two matrices, A and B, are they inverses? Right? This is a yes or no question. Are matrices A and B inverses? And how would you go about finding the answer to this question? Well, here's all that's required. You don't actually have to know how to find an inverse to do this. You just have to think about what would the result of A times B and B times A look like. So if you were daydreaming the last 10 minutes, remember we said any number multiplied by its multiplicative inverse is equal to 1. So if indeed A and B are inverses, then what we should expect is that the multiplication of A times B gives us the identity matrix. So that's all that's required at this point, is for you to go in, do A times B, then do B times A, And what you should get in both cases is the following. So yes, they are inverses. And now, example 2, how do we actually use that formula to find an inverse? And remember, this is only for a 2 by 2 matrix. Not 3 by 3s or 4 by 4s. By the way, it should go without saying that if you want to be able to find an inverse of a matrix, you are going to have to require that the matrix be a square matrix, right? That it be a 3 by 3 or a 2 by 2, 4 by 4. But right now the question is, given matrix A, can you find A inverse? All right. So let's go through. Let's just use this this formula to find A inverse. All right. So I'm going to go ahead and label. So in this case, A, B, C, D. What are in these entry positions? So in the entry position for A, we have 3, 4, 5, 6. Okay, so to find A inverse, we're going to have 1 over A times D minus B times C, and that is going to end up being a scalar on the outside, right, on the outside of the following. So you can kind of notice the changing around of the positions and signs of these entries. So now we want D where A was. So that would be 6 here, negative 4 here, negative 5 here, 3 here. All right. So if you run, so the determinant of that problem, the 3 times 6 minus 4 times 5, gives us I believe a negative 2, right? 18 minus 20 is negative 2. So we basically have negative 1/2 on the outside of this matrix. Now this is not the inverse. All right, we have to then distribute that negative 1/2. We have to scale. And so if we a negative 1/2 of 6 is negative 3. This should be a positive 2. Let's see, this should be a positive 5/2, and this should be a negative 3/2. All right, that is A inverse. Now, if you were taking a test, taking a quiz, homework, and you were second guessing your work, well, go back to what we did up here in example 1. You could always take your proposed solution, multiply by the original matrix, and confirm that you actually do get 1. You do get the identity matrix. All right. So I mentioned the idea of using the inverse of a matrix to actually solve a system. Right? So this is fairly interesting. The idea that here's another system that you already know how to solve this, right? We've already determined that you can place this into a matrix, right? An augmented matrix that you can row reduce. Okay. Well, what about if you want to use the inverse of A? Or maybe let's start with what the heck is A in this problem? Well, we think of A as being the coefficient matrix, and we think of B as being that last column, that vector column in the process. So in this case, A is just simply a 2 by 2 matrix, 3, 4, 5, 6. Now we've already gone through and found the inverse of A. That was in the previous problem, right? So I'm going to see if I can recall without going back and looking. But I think in that example 2, it was -3, 2, 5 halves, and -3 halves. Okay, I hope that's legible. So let's get back to where we are in this problem. So we have matrix A multiplied by x is equal to b, right? That is, let me come down here. That is the way the problem sits right now. What do we want? Well, we want to know the values of x sub 1 and x sub 2. We're not going to row reduce, although you could always double check this with the row reduction algorithm. Instead, what we're going to do is we're going to multiply both sides of this equation by the inverse of A. Let me rewrite that because you actually don't want to get too sloppy with that. So A inverse times B, right? So we're basically multiplying both sides of the equation by A inverse. We already know what A inverse times A is. That's just going to be the identity matrix. So that's just 1. 1 times x is x. And now what I'm going to do is I'm just going to kind of drag and drop the inverse of A in here. So -3, 2, 5 halves, -3 halves. Okay, and then I'm also going to drop in my 3/7 for B. All right, so structurally, can we multiply this? Well, this is a 2 by 2, and we would be multiplying by a, now I don't know why I wrote that as a fraction. My apologies. So that's 3/7. So structurally, we got a 2 by 2 multiplied by a 2 by 1, so that is, we can definitely perform the multiplication. The result should be a 2 by 1 matrix, or 2 by 1 vector, actually, and that answer is 5, -3. What did you just do? You just figured out, right, the goal of this problem is for you to solve the system, right? You didn't use the substitution method, elimination method. You didn't graph these two lines and figure out where they intersect. We didn't do all that work that you did in high school. We didn't even use the row reduction algorithm that's in our calculator. What we did was simply use the fact that the coefficients over our variables can be thought of as a matrix, and that since it has an inverse, we can use that inverse to find the solutions. X sub 1 is 5, x sub 2 is -3. That is probably the greatest thing that you've ever done in your whole life. That I know to be true. And I know you're in a in waiting to figure out about this decoding problem that we're going to do, and you're going to have to wait until the next video. See you soon.